did fit very well into our, I would say, our daily job. And the more I look at it, I see that electrical and mechanical, it's very much aligned together. And one is not probably, it might be a bold statement here, but one is not anymore pure, one, separate line saying I'm just a pure mechanical or I'm pure electrical. And the reason I'm saying this, it's kind of a quick intro to my work here in the sensor concepts and sensor developments, sensor data fusion. And this leads us to very high, kind of introduction here, which I like to mention, upfront here, that my goal is not to teach you today or share with you mathematical formulations or integration or double integrating, whatever is those, sophisticated math. I'm sure you are already more advanced in that, and probably some of you may be already sick of doing this daily. But I will be more kind of the applications of the sensors and the sensors data, and how can we make use of this data or of these these elements. In one, just if you think for a second here, as in my slides here, what is the sensing systems? And think about it, whether in your car or in your house or in your daily applications in your lab or anywhere, on your phone. It gives you simply, gives you kind of alert or information about what's changed around that property that you are sensing. If you are speeding, driving on your car, you see your speed is changed from whatever number or kph or mph to whatever new scale or level. If you have a temperature sensor, you see, okay, the temperature out, it's the 52 or 32, etc. So you basically looking at how much the change is. Now, today, this used to be just used to give just things change, up to you as a user what to make or what this. It's like a red flag, yellow, green color, whatever is those communications. Now we are taking this data, whatever we are seeing out of the sensor, and as the two examples I just mentioned, if you have the temperature outside is 30, and you set your thermostat in the house or in your car, the HVAC system, saying it has to be, the temperature has to be maintained always around room temperature, something around 68, 70, evaluate that, then that is going to give a message to your system to control on your system and to kick off the whatever heating system you have. And it brings up the temperature to the environmental temperature that you are controlling. Now here's, so you from this data, you were able to make a decision what to actuate and what to monitor. If you think further on this one, you might look at every the morning and need to run my vehicle, and I need to make sure my engine, my vehicle is warmed up. So you took this information, the examples I just mentioned, to a third level, where you now said to your system, one temperature, what's the time when the time comes to this 7 o'clock, and if the temperature, the outside temperature is around this time level or below this threshold, and I need you to turn on the warming elements in my driver's seat only. Somebody else who wants to turn also the other seats or the entire heat the entire cabin. But again, at the same time, you will say, you look at this as kind of a prediction and monitoring for something in the future to come. But at the same time, you are telling your system that if the power in the battery, if this is a battery, if this electrical vehicle or even normal vehicle, if the state charge on the battery is below this threshold, don't do this action. And send me a message to my phone to do or to make, kind of additional actions on it. So I might just, kind of do bring further information or further activities on the vehicle or ignore some of the commands that already programmed. The examples I'm going through here is just to give you kind of where we are, how we are traveling in the usage of the data, and what kind of, after you use this data, what kind of information we make out of it. And I want to just be clear, I'm going to hear you.
Dr. Ghanam, can you please turn off the video so we can hear you better? The sound is a little bit cutting off sometimes.
Yeah, this is expected with, as I mentioned, so it might be a problem. Let me double check that, yeah. Hopefully it will be better now.
Initially, it's better now. I can hear you better. Yeah. Thank you.
Sure. So I want to just kind of repeat the last sentence I mentioned about that is the data. When I say data versus information, the data, think about it as numbers or signals coming from the sensor through a certain controller, versus the information is what you make out of this data. So you get a signal coming from a sensor, but now you run this signal into your algorithms or whatever measurements or system you are using, and you providing now a new type of data, which is, I'm calling it information here. Like, for example, the weather is hot, the room is hot, or the room is cold, or the vehicle is, you are over speeding or under speeding, etc. So these are kind of the information I'm looking at it. And this is where it's gonna come in the rest of the discussion about the data fusion. Usually the information comes as a combination of multiple inputs from different sensors, or the processing signals like acceleration, you get the local speed, displacement, for example. So this is kind of just kind of a very, I'm sure, sharing this kind of description, or at least to this seminar or this discussion, what's the difference, or what I mean by data and what I mean by information. To move on here for a second step here, just when we say sensor or sensor system, think about what kind of properties we are measuring or changing. And I assume most of you on the audience are engineering, to the best of my knowledge. So in that area, on that field, you are measuring the mechanical behavior, not only from mechanical elements itself, but the mechanical behavior that around the uncertain control volume or control, spatial. The sensing element could be as just a simple bridge, and one of the resistors, when she sees different, kind of gets under different influence or impact, it changes the output voltage, and you start reading from that what the sending that as a voltage change or message. And that is going to be taken to the second level, where you will be connected that to a circuit or a device to read that and to make information for that. To take this to applications, sensors, just you could look it up. You could think of all kinds of sensors. It's not just a temperature sensor, as an example I mentioned, or accelerometer, or any of those. But you could think of what I can use this in my applications, especially in the auto industry. Always, the first example is going to come to your mind is that most advanced usage of this is in the autonomous vehicles. Autonomous vehicles is very much you are relying on these sensing around the distributed on the vehicle, collecting all the information from all these sensors, fusing it, making new information prediction, what's about about the route, about the speed, about the direction, what to turn, what to actuate, what signals or what to brake, or etc. And if you look at just the normal car that you have, it's not also it's not something that relies on less sensors or not appreciated level of sensing systems, but it's also fully loaded with sensors. And in matter of fact, I always kind of joke, it's almost every single surface on the vehicle has a sensor, and that sensor could be for vehicle actuations or vehicle applications, or to customer usage or convenience. Examples on that, either you need a sensor to tell you what is the level on the fuel, or you need a sensor to tell you whether the door ajar switch is open, the door is open or closed, or or alert sensor or a message to tell you put the seat belt, or the seat is empty, kind of adjust the seat in different way, or turn on the lights and so on. To give another, this is kind of given that I'm from auto industry, but it's that's not the only thing we use the sensors for. Think about what you have in your mobile devices that you are carrying every day, and how those are connected, and how those are making your life, more easily to handle multiple tasks, and to to optimize your time and your day with these devices, hoping for the enjoyments and productivity. The simple way to think of this is you have these devices, whether they are phones or whatever they are, whatever information you see on the screen, it's appreciation and good to the software ability and the computational power on those. But if you look at your phone that you have, to my understanding, it's at least 12 sensors that gives you the just kind of very much those are in your use, in such as your movement, the cameras, the sounds, on all these kind of applications. So these are kind of just to get a flavor where only when you if you think about the sensor, it's whether it's in the mobile device or in a vehicle or in an airplane or in a ship, it carries the same fundamental understanding from electronics and behavior, and however certain device, certain range different, certain characteristics are different, but need is similar, and the usage is almost the same, and the benefit that you take out of it in general terms, yes, it is same. So now if you bring those into the mechanical system, again, where we need this and what kind of application, we can count many applications or needs, but this is an example what you see in your car, an example in a car here, on very high level, what kind of applications you might use this for. As you see here, for example, the active suspension systems in the car. If your vehicle is coming towards a bump or something in the road, some vehicles, they have that adjustment suspension system. Or if you need just to look at your steering, that the one you steer your car with, if that steering with certain power steering systems and sensors, you'll be able to control the steering with less input, with more secure process. And at the same time, it's very important that the steering angle that you are steering your car, it will be shared with other systems in the vehicle, and it will be very useful for those systems to make decisions about it. And to say that you are, on lane, within the lane or out of the lane, or what kind of braking or rolling, etc. These are just kind of, again, applications where we are looking at, thinking of that good examples to make appreciation of the need of the sensor. And the thing where, if you are running a fluid mechanics model or analysis on this picture here, and you're running the flow on the vehicle to define the drag, to define all those relevant fluid mechanics applications. Think now each one of these element on the display as in your finite element analysis or finite volume if you are running fluid, and this will be a monitoring point. So if you, the more you get of these information, the preciseness of your airflow measurement would be. If you are looking at this as stress strain analysis, for example, the more you refine these elements, you could be able to define how much local deformation or stresses or any of those also occurred, or what's happening at each small element of these on the surface, and how this can be transmitted or transferred. I brought those two examples, fluid mechanics and the fluid and solid mechanics here, to relate some of those applications, direct applications for sensors, where you can use them into your design and cascade this down to how can you build whether a surface that that provides you the optimal design, optimal design and performance from, for the drag or from the driving from that perspective. Or if you are looking at this as stress strain or as the dynamic behaviors, durability or reliability, etc., those also can be cascaded, those sensor behaviors on your vehicle while you are driving, and make a decision based on that, whether this design is meeting whatever requirements you have, or it's predicted to have an issue down the road. So the just mix two things here is talking about this as a front element or finite volume element, in a sense of if you are doing simulations, think about each one of these elements or nodes. When you take the time history, think of it as a sensor. And if you are doing this on physical testing or lab, think about that. The more sensors you have, the better of the data you might be able to generate. Doing either way, I don't expect we are mechanically, physically, we are to distribute sensors everywhere here, but can we design the sensor to cover more area rather than just finite element area spot or small element area, space or a surface? And think about this: if I have only a temperature sensor sitting at one of these nodes here, versus that's going to give me the local temperature here, and depends on what kind of metal or material of this surface, might give me the temperature distribution farther down here. But if I have a thermal image sensor up here that has a wide view that can cover the whole surface, now from this image sensor or this thermal camera, I can get a wider distribution for the heat, for thermal on this area, on this zone. I brought these two examples, just to kind of think of two dimensions here. One is, if I have more nodes, more sensors, definitely I will generate more data, and I'll be able to make better information, and get very fine distribution, whether for any parameter I have, whether pressure, temperature, volume, anything, density, etc. Or in the other second dimension, rather than adding sensors, can I get more advanced on my sensors themselves and change them, modify them, use different types that can provide me wider range of information with less number of sensors. And this is true not only in auto industry, this can be in anywhere, in any application you might have. Is it true always more sensors or different types of sensors? So this is another example, just kind of, if you think this heavy machine floating on the ocean or on the water is, imagine if you do not have this, you could throw this just, on, as I don't believe Noah was the first, when he made the first, ship, if you want to call it, he put any sensor on it, just, he put that on the water, and, and just floated, and just let the physical behavior of the law of the physics, just let the system flow and make it, just flowing based on that. But now with this bigger machine, I mean, with this machine and with this more need that you are looking for, whether the comfort of the of people on it, or to make, kind of speed, make adjustments in the directions on how fast and where to stop or where to move, and prevent other conditions, or accident, or interacting with others. Anyway, so the idea here is that more sensors to this system is needed, not for motion, it's also for the applications that coming out of it. And I want to, kind of the twist here is, think about these vehicles, whether it's a car or this machine, this ship. Their sensor's job nowadays is not just provide information to itself. If you hear often nowadays saying mining data, we do say mining data for something like some for digital currency or any of those stuff. But imagine now, like people are doing the YouTubes, or doing all these kind of fast, quick information, and gaining some benefit, financial benefit out of this. Let's just focus on that part for a second. Think about these now, whether it's a ship or a car or airplane, or you as a user carrying a cell phone, your sensors now grabbing information around you, from how's the temperature at that point, how is the weather, what's the scene, nice scene, or views, or if there is any dangerous conditions, and you broadcasting these information, and how others receive the information and make use of it, and they basically, you provide data and they give you money or benefit, basically compensate for your effort. Good example, if you use some of those track maps, or any of those, whether Google or others, that you start seeing if there's a traffic at some point. That's most of the time from people inputs, some of them, or from some sensors already fixed on that location, or from on vehicles and moving vehicles, and sharing the information to other users. So my point here is, think about now, sensor is not used or need their applications for the device, the specific device or machine or person that using them. It's also providing this data and sharing it to others, that to make more use of it, and that is where we are going with what's called big data now, and where we are doing the cloud information, and where we are taking that to higher level, and sharing the data to not just compensate, get compensation for that from benefit, from financial benefit, but also from prediction next steps or preventing any kind of wrong conditions or services. Showing another example in the aerospace, and a good example, I brought this for a couple of things. One is to also appreciate that mechanical engineers or civil engineers, they put all these nice designs and all these kind of optimized mechanisms, but at the same time, you need the sensor system to, sometimes you need to do kind of mechanical, dynamic, or transfer directions in the design itself. In other words, if the wing, as you see in this airplane, you might need to change the angle or change something to provide optimization to the behavior of the, or the performance of the unit. One thing also need to be careful about it, when you design your sensor, every sensor has its own limitation, any sensing systems. The sensing systems limitation could be just in the range, saying this sensor measures between -20 to 150 as temperature, or from this pressure to that pressure. So that is upfront is known. But the other, you put that in the sensor design. But as an engineer trying to apply and utilize this sensor, think of what application you are using this sensor for. So are you going to use your whatever design you are making, is it going to be always within this range from atmospheric pressure to certain atmospheric pressure, just this sea level or and above, or something below the sea level pressure, for example? If you think about any airplane like this, you would say always the airplanes are in general are above, they are functioning and they're flying above the sea. So my design simply as engineer is just, I need to have, something like any algorithms or analysis has to be within this range for some applications above the sea level pressure. I was, as I mentioned up, earlier in my introduction, and that's why I brought that example too, is I'm originally from Palestine, and when I drive from Jerusalem down to Jericho, you hear big drop in your, big pressure on your ear, because in your ears, because you are going down to the Dead Sea, and that Dead Sea is, as far as I know, point of, and the pressure down there is much lower than the typical level. And I was taking time, and that's something called functional safety design and systems. And during the training, in one of the functional aspects of our sensors was pressure sensors. On some of those airplanes, with some maneuvers down, and they were low on the sea level down in the Dead Sea level, and the pressure sensors, they start acting like crazy and funny, and all kind of errors start coming on the screen, and the screen back and forth, repeated the experiment, the maneuvers. They realized later on some of those pressure sensors on the vehicle being designed as the example or the use case that I mentioned earlier, that this is more
Dr. Ghannam, we cannot hear you. Are you?
Sorry, I think I touched the mute by mistake. Do you hear me now?
Yes, we can.
So I was about this use case where when you design the sensor, you need to make sure the environmental that this application will be used are expanded, and make sure those are not something. Don't assume everything is within just that range unless you make your good analysis into the what's called nowadays functional safety. I'll leave some of those students, those who kind of need to look into this in the future. Look what some these are new standards, and it's like failure mode analysis, but it's called now functional safety. It's good to have some kind of background about it and help you in realizing how things now in the electronics and how people they analyze them and look at them. This is again another area. Mechanical engineers, they put all those joints for all these systems, all these integrated motions. But again, you need these kind of radars, lidars, or just simple, sensors and on the steps, on the pressures, and so on. Another thing is, again, transportation is. This is another, think of it as not just a seat belt and comfort in the seat. Think of this as the ergonomics, and think that to make sure all these not creating, especially those who drives or flies long flights or drives long trips. You want to make sure you have sensing systems that provide them or measures their behavior and reflect on that and provides recommendation about the design. And not only that, is even upfront when you design the system, you need to run the system through all these kind of examples. This brings me to something I mentioned in the title of my this seminar in the last few minutes here, the safety. Was part of my job in the old days. I was doing, kind of certifying, running different systems, analysis, behavior, sensors, all these things that running, evaluating them before the vehicle hits the road, or certify the vehicle before it goes out. And this is typically what's known in the auto industry. It's self-certification. So the governments, they do have their requirements. And as safety, as an OEM or any organization, need to bring a product, you need to make sure that your product is meeting all, does meet all these requirements, and you have to show the documentations and all the requirements are met through the provided tests. So for that, there are different kinds of testing related to the crash and specifications of the occupants, small size, medium size, large size, and some people, they call them 50th or 95th percentile. Children with different ages, and in car seat, and so on. As I mentioned, the self-certification go through against multiple types of tests. Some of them front impact, some of them side impact, and each one of them, they set up the vehicle again, various front data, and measure the responses on each one of these occupant or these dummies in this case. And based on that, they decide the pass-fail condition. This is again another example. If you look at FMVSS under Federal Motor Vehicle Safety Standards, look at under NHTSA or FMVS, NHTSA or IHS, take a chance, just the grip, look at under those and see what kind of tests and how those, you will see lots of YouTubes and information about that to give you appreciation how sometimes the milliseconds of breaks it. Milliseconds in the deformation of the structure, the deformation of the train systems could reduce the amount of the energy or forces that the occupant sees during the impact, and that could be a saver, a big saver to their conditions. In the gain in the crash, when I mentioned here, I mentioned the restraint systems, those airbags, those seat belts, suspensions or braking, active safety, or any of these, and those you're talking about milliseconds. I repeat that, kind of for the importance of having those correct in a sense of whether in the design or in as a user to be in the right position if you based on your size, or to be buckled while you are driving, or to be kind of some people, they could give you kind of good example. Passengers sometimes they put their feet on the dash, and this is as example of out of position or something. It's not only design, but it's also a use requirements. I mentioned the passive safety. Which is, when I say passive safety, think about the what kind of what safety features or activations would occur during the impact versus the active safety pre the impact. What things you could do in your car, what the car does for you to prevent any of these kind of impacts, to stay in the lane, to slow the speed, to reduce the gap between the cars. If you are backing up, to make sure there's nothing behind you. If you are trying to park, your parking aid sensors start beeping, and so on. The title, as I mentioned, fusion, the data fusion and sensors fusions data and etc. You could combining etc. The reason I want to just bring this in trying to close with this, if you, as I mentioned earlier, mentioned several types of sensors, whether it's like a sensor like just a thermal sensor, temperature sensor, accelerometer, or as something like LiDAR, IDAR, which is active sensor, basically that pulse laser to measure the range, or camera, which is those those are again another type of passive sensors that extracts basically the lights, the visible light, I should say, from the electromagnetic spectrum around and makes use of it, or radars that we are familiar at a certain point, or at least we hear always about in the airplanes and different applications, which is another active sensor, another type of active sensors that use the frequency modulated waves and waveform, and will be and typically used to detect any moving targets or applications. And among all of these, now, if somebody say I can everything, or I can use radar for everything, or I can use or answer for everything, that's become debatable questions, not just debatable. This is the big issue now, is you need every application functioning and working. In order to be able to do that, you need to combine those and make use of them. And that's where a few sensors using data, and that is where the future nowadays, collecting all the data, mining data, combining different sensors, and sending it as a big data, as to cloud or big data, and apply what's called AI/ML. AI/ML is a big deal nowadays, and definitely it's not, I would say, only for electrical or mechanical or in a certain field. I do really encourage everyone, and this is where if you tell me from this whole seminar, I would kind of emphasize again, beside the sensors and grabbing some knowledge on the sensing systems and their applications, and the data, their data processing. The third piece I would look at it is think about the AI ML applications as a tool. Think not more is just a field. Think about it as like using your computer now is a tool for this communication or this kind of process services. Think about the AI ML as a tool that you need in your, no matter what application you are using or design you are using. Think to use that get your hand or your feet wet into that field. It's needed for several applications. I'm showing this is just another example of sensing systems to prevent pedestrian impacts or injuries by deploying or raising the hood to increase the gap. And again, this is where it becomes sometimes whether the sensing on the vehicle or the information coming from the cloud or the big data I just mentioned to tell you, hey, by the way, there is some occupant, pedestrian, this street or this area is busy, slow down, or vice versa. If the system did not tell you about this and all of a sudden a deer or something, somebody jumped ahead, how can you make this less severe? Data fusion, again, I jumped earlier, and this is an example where I was talking about, as mentioned, the examples of the sensors I mentioned. In this case here, you have a radar in front of the car, and that's short range and long range. Each one of them provides advantage. The long range has a smaller field of view angle versus the shorter range, bigger, wider. And you have accelerometers sitting on the center of the car, and again, and you have front crash sensors up front, those are down here. And the data that's coming from all of these, it tells you two things. It tells you if you are near to impact vehicle, or if your vehicle near to be damaged or hit, or it tells you if your vehicle needs near to roll. And even if the event occurred, then it tells you, as you see here, just by taking the sensors data from multiple sensors, you could say, without knowing what's the vehicle speed and reading the vehicle, tell this is the signal from this kind of crash or impact for against rigid barrier RB here with 16 miles per hour, versus if I am hitting a soft rigid barrier with 40 miles per hour, this is a signature of this type of sensors or information, versus this is, for example, angular front or left angular 30 mile per hour, 30 degree at 25 mile per hour. And the reason I brought this here just to tell you, because when they deploy those bags, they deploy them based on these events. For example, the 40 mile per hour detection airbag deployment will be, let's say, at 40 milliseconds. Versus the 30 mile per 25 mile per hour angular, that could be at 25 milliseconds. Versus, for example, this may be no deployment. I'm just going. These are examples. Don't quote these as these are how it is. I'm just giving you. They are based on these and signal. You make decisions. This is a good example for rollover. Example for the multiple inputs of the different sensors when I mentioned earlier about fusing data into the safety application. By knowing its lateral acceleration and the angular rate, it would be able to detect whether the vehicle is going to roll or not. And if it rolls, I need to deploy the side curtain from the roof, those other, or take certain measurements to protect the occupants. So this is an example where you've used multiple multiple data from different sensors and make a big significant decision to protect the user. So with that, I think we are almost there in the time-wise. I was hoping to finish before to give you more chance for questions, but let's see if there is any question here.
Thank you very much, Dr. Ghannam. Very interesting high-level talk. So if you guys have any questions, please put in the Q&A, or we can unmute you to ask questions. Ala, would you like to?
Yeah, hello. Thank you, Dr. Ghannam, for the presentation. I just have one question. With the increasing, applications of sensing and applying more sensors in the vehicle, especially with the autonomous vehicles, how reliable you think all these systems and their integration can be for the safety? We have heard multiple incidents where the autonomous vehicle basically didn't sense that the person who's on the street, and then they actually run over him or her. So what challenges you feel and that will solve this problem, especially in terms of research?
Very good question. And this is, I know those incident, the incident that, did get into the media and in the news about some of the OEM that has that, couple of issues or etc. But you have to think about this. If you look at the research so far, most of the research does show that the AV will be safer than the manned driving people in general overall. Because if you look at the failure modes of the people, when I say failure mode, people get distracted with many things, and how many accidents on the roads and conditions. There are so many. I'm not trying to justify one or against the other, but I'm trying to say those conditions do occur, the failures and the systems, and that could be either on the limitations of the sensors themselves, as the example I mentioned with the airplane on the Dead Sea example, or could be in the algorithm and the software, which is most of the time algorithms. And I was listening to another the other day seminar or lecture from somebody talking about predicting the unpredictable. When they say artificial intelligence, you run this, develop this artificial intelligence systems, at some point those might start behaving in something new unknowns. So you need to kind of make sure, as I mentioned, the functional safety and failure mode analysis, those being designed upfront and analyzed. Challenge could happen, always could happen, I agree, but definitely the research community and in general, everybody, especially when it comes to safety, there are very stringent requirements and has to be met, and no reason for, no excuse for any failure.
Thank you. I have questions for our speaker, Dr. Ghannam. I have two questions actually as well. So one is more or less related to what Ala was saying, but we all saw what happened in Texas when it came to extreme weather conditions, right? And it was unfortunate seeing that, but I noticed that there were a lot of cars that they had a lot of modern technology, I assume, such as LIDAR and radar. So what are the things that you guys are doing to ensure that these basically sensors are going to operate properly when it comes to extreme weather conditions, or when it comes to, having dirt or snow or anything basically on the road that accumulates on them? Because I personally experienced when I drive in snow, all these functions basically they don't work. So that you need to stop and clean it, otherwise it's not going to be available. So what are the things that you guys are doing to address that in terms of these sensors functioning properly in those weather conditions? And the second thing is, second question is kind of a personal experience. So when it comes to these, let's say if you want to use adaptive cruise control, in the curved basically roads or interstates, it is acting still a little bit funky in a way that it doesn't really notice the curve and it doesn't really adjust the distance based on the vehicle exactly in front of your vehicle. So what are the things that you guys are doing to address those?
This is very good question. That when you design a system, number one, you have to make sure there is redundancy and there is always quality or for any design or any system you have, especially when we talk about safety. And if you talk about safety rating system, you have to have always like a backup, in a simple way to say it. And the backup usually is either you take information from another sensor, because the sensor could fail due to could be due to it's a failure on the sensor itself, or due to challenge condition outside, the examples you mentioned. And we know, for example, the three example sensors I mentioned, LiDAR, camera, etc. Each one of them has pros and cons. Like, for example, LiDAR, it's expensive, and no appearance for information about it, or in air, it has a rotating part, and that could be degraded due to the examples you mentioned. Or the camera, we know it could get dirty very easy and blocked, because it relies on field view, the lights. But that's why if you look at the autonomous vehicle, it carries all the above. It carries all these sensors, the examples I mentioned, in additional to the GPS, in additional to accelerometers on the vehicle itself, measuring, kind of doing additional kind of calculations where the vehicle starts from and where the vehicle, and where kind of analyzing where the vehicle is at or around. And all these information to come together becomes here where the software and the application and the algorithms, the AI that's mentioned before, the artificial intelligence and machine learning, that's where it becomes very handy now. You have all this data, and not relying only on the performance or degradation of the performance of the sensor itself, but also in the the analysis and the history that you train the system on. This challenge on the sense with the environmental challenge, Mother Nature is, no matter what you design, always you're gonna face these challenges. That's these facts. But definitely there are during the design, always there are a backup or kind of limp home conditions that we try to analyze, at least to bring the vehicle to a safe stop or safe condition. Might not ride you or give you all the ride for the to the end, but at least to bring you to a safe stop or safe condition.
Thank you. So about that, we have a couple of questions, but just quickly. So this adaptive cruise that basically doesn't work properly on the curved roads. So you guys are working to address that as well, in a sense that basically it doesn't properly detect the vehicle right in front of you, which is basically a curved condition, whereas it's basically seeing the vehicle that is a little bit ahead of you, but next to you.
Yes, it is. It's the gap clear and relative displacement. Again, what sensor will be used for that? If you are using like radar, for example, and if you're in a curved condition and your radars field of view, the examples I showed here, they have different kind of angle. They do align. This is, as I mentioned a few before when I said the steering wheel. They mentioned GPS. This is exactly where the again, or the algorithms, not only AI, but the fusion, the data fusion here. You grabbing the information from the vehicle, whether the vehicle is on straight or not. You grabbing the information from the GPS, tells you if this is a turn, and you grabbing the information from the wheel, the sensors in the wheels, to tell you the level of the vehicle. Are you on a flat surface or in kind of tilted surface? and which is, you could get that also from, there's a role in the RC, the center of the vehicle, there's kind of a roll rate sensor. And like you have also the yaw, how, kind of twisting the vehicle, or the pitch front, up and down. So you get all these information together and you stitch it and you make it, kind of, you adjust the measurement that you mentioned. This is really X number of feet, or it's X number of feet times this factor because of these ankle, kind of turn or curves conditions.
Thank you. I have a question from Bilal. He's asking, with all this technology present in vehicles, this makes the vehicle an easy target to be hacked. How's that being accounted for?
It definitely is a good question, and this is always, if you think about it now, it's always a challenge. Hacking the vehicle, whether in the old days, just breaking the doors and getting and turning on the ignition or connecting some wires, or hacking the software and taking control in the vehicle, or pushing some bugs into the vehicle system. It's not different from your phones that you have, or your computer system you are analyzing, or your house, your smart house systems. There is lots of security layers, and in the software, and in the hardware, and there's tons of efforts just in the security area, and to making sure the transmitted data from to the vehicle are secured. And but always there's challenge. We get smart in the design, but others, they get smart and unfortunate in the other side, and something could happen too. But
Thanks.
This is just, yeah, sure, there is it's a good question.
Yeah, thank you. So Jamal has a question about the preference from your experience for a LiDAR versus using cameras for autonomous driving. So some apparently use LiDAR, some basically use camera and radar, at least based on the question Jamal is asking. Based on your experience, which one you prefer?
It's yeah, I know what you talk about. There are some suppliers, some OEMs, they claim at some point they will use only cameras, and some they saying LiDARs and cameras, but I will leave this as such. You, at the end of the day, whatever sensor you're gonna use, or multiple sensors, which is, I am always a big fan of if, it depends what application again. There are certain requirements, and you need to demonstrate, as I mentioned, those requirements being met. Nobody from whether governmental or insurance or anything challenge you in a sense of what technology, what type of sensors, or how many sensors to use. They challenge you as whether you are meeting these requirements or not. So if somebody is able to do one sensor, if I'm kind of laughing at this because you could tell one sensor is a challenge. So, but at the end of the day is what's the performance that's shown on the system, and you look at those net side, the one I showed, or HS, you could see the rating for each vehicle and each design.
Thank you. Any other questions? Last minute comment or question? Ala, do you have anything to add?
Thank you, Dr. Ghannam. I have just one question. For future employee that comes out of fresh from graduate school to be hired within this field in auto industry, what skills you feel that you look at when you consider an applicant for these positions?
I'm really glad you asked this question, and this is where I want to kind of if you ask me, from this entire presentation, I was intending to inspire the engineers to look at these additional three aspects. One is the electronic gel, their mechanical understanding. Two is the AI ML. That's another piece. It's nowadays is one of those hot, I would say, items. And as I mentioned, it does not mean you have to be expert in either or as a mechanical engineer. But if you are a mechanical engineer and did some projects with relevant, with some kind of electronics, data analysis, and some of these applications, that will be a big plus for your resume, and it's good to have under your belt and to demonstrate the expansion of your knowledge. It's not anymore just solid mechanics or fluid mechanics. It's where and how you expand those. I did my PhD and in fluid mechanics. I did kind of aerodynamics. Did solid mechanics. I taught different courses at different universities in different fields. I still centered, mechatronics. That was one of the favorite class I taught beside my other, classical mechanical courses. Did, in matter of fact, one time I did teach course at Central University. It was supposed to be kind of the graduation course. And instead of being on auto, at that time, this was about 6 years ago, I focused on the drones. And later on, quite of the students, they were kind of appreciating the course and sending notes that, hey, drones is kind of the future now. And they start putting, getting some just from that course, even they were mechanical. So my point, just to answer, your question in a short, is please, for those students hitting a job in the market, make sure and somehow to touch on the electronics, AI/ML.
Indeed.
I have a graduate student working with me, actually still working till today with another university on a project. He just finished his PhD and he got offers, right? 2 offers actually. Definitely a good student, but he is, I would say, at the right time with the right experience, as I mentioned.
Thank you very much. Very good question, and indeed great advice for our grad students for seeking multidisciplinary, interdisciplinary skills. I guess that brings us to the end of this seminar. I would like to thank you again, Dr. Ghannam, for this great high-level presentation and accepting our invitation. And I hope to basically get the chance to see in future. And we get many thank yous from the presenters, from the audience as well.
Thank you so much, Dr. Ghannam.
Sure. Likewise, I appreciate your invitation, and please feel free to reach out if you have any other, question, especially for those students who have interest in certain, whatever I can, I'll be more than happy.
Thank you.
Sure.
Thank you.